Okay, section 2 deals with gas laws. There's like 3 different laws that we cover in here, or maybe actually technically a 4th one. 2 of these laws we already went through when you were in physical science. So in other words, they were easy enough for freshmen to understand, so you're juniors, you should be able to handle this. These gas laws give us some simple, as it says, mathematical relationship between these quantities: the volume, the temperature, the pressure, and then the quantity of gas. And by quantity we mean like how many moles. Some of these laws are just between 2 of those, and we're assuming that the others are kept constant. And then we'll end up with finally one that will have all 4 of those in one equation, which, as it turns out, often is the most helpful one at the very end. It sounds like it'd be more difficult, but it's not. Now, gas and volume, volume and pressure are inversely proportional. If I compress the gas, it's going to have less volume, but it's going to increase the pressure. Robert Boyle is the one that discovered this. He discovered that if you double the pressure on a gas and you kept the other factors constant, like temperature and how many moles of gas you have, in other words, you're not changing the number of atoms or molecules, and you keep the temperature the same, that the volume is going to become half as much as it was before. So if I double the pressure, or in order to double the pressure, I have to decrease the volume to a half what it was before. And to explain this, we can use the kinetic molecular theory that pressure and volume, to help us explain why that holds true. Remember that if I want to increase the pressure, I need to make them collide more often, right? Well, how do you increase the number of collisions? How do you make them bump into the walls more often? Well, bring the walls closer together, right? So if we would, and I think if this analogy sometimes helps with that. Imagine that we had the number of people in Omaha, same number of people, same number of cars, but now we make Omaha half the size that it was before. What's going to happen to the number of car accidents? It's going to increase, right? You're going to increase the pressure, the accident pressure, if you want to think of it that way, because there's going to be a lot more, it's going to be a lot more congested. Sort of like if you would go to some of the big cities like Dallas and LA and New York, there's a lot more cars on the street. Chances of an accident are a lot greater. But even in the early days of the automobiles, there was one county that only had 2 cars, but they managed to crash into each other. Only 2 cars, but they managed to run into each other. So that isn't doesn't, reducing it doesn't keep collisions from happening. They have drivers. The pressure of the gas is caused by moving molecules hitting the wall, right? We said that to create pressure, you have to have collisions. And if the volume of the container is decreased, the molecules don't have to move as far before they hit a wall. So it's going to create more pressure if I decrease. Now, we're not changing the speed of the molecules. That's what temperature does, right? Temperature is related to the average kinetic energy, which has to do with speed. So we're not saying these cars are going to move faster. They're just going to run into each other more often because they're just closer to each other. So what you're having then is, in essence, a larger number of molecules per unit volume. And so if you have more molecules in a certain amount of space, they're going to collide more often. It just makes the common sense just tells us that's what's going to happen. And if they have more collisions, you have more pressure. So in this whole thing about gases, think about collisions cause pressure. Collisions cause pressure. You're going to be doing a lab next week that has to do with Boyle's Law. You're going to be measuring the pressure of a gas at different volumes. We're going to be using our little handheld computers that we use for those things. And then we have a gas pressure sensor we're going to hook to it. And we're going to put a syringe on the end of it that has volume in it that we can adjust. And if you measure these pressures, you're going to end up with a graph similar to this. Notice it's a curved line. Now, if you look at those charts that are across the top, which one of those charts has a curve similar to this? Isn't it this one over here that has a curve that goes down like this? So that's an inverse proportion. Now, if it's an inverse proportion, it means that, A is proportional to the inverse of B, would be another way of saying that. But another thing is also true. Notice, A times B is always a constant. So if I look up here, notice they have pressure 100 and volume 500. If I multiply those together, I get 50,000. And if I take the next number, 150 times 333, I get 49,950. Okay, it stays pretty close to the same, all the way down like that, right? So their product is a constant. So that kind of tells you a little bit of what this equation possibly will look like that relates these two. Now, this is assuming that the temperature doesn't change. Because usually when I compress a gas, it gets hotter. Some of you have used an air pump, a handheld pump, to pump up like a basketball or your bicycle tire. I don't know if you've ever felt the pump after it was done, it felt hot. So it generates heat. So if I want to actually make my measurement in that situation, I would need to wait until the temperature in the gas got back to its original temperature before I read it. Otherwise, I've got more than one thing going on here, and that's not good. So Boyle's law states that the volume of a fixed mass of gas, okay, so they said that the quantity of gas, the quantity of molecules is fixed, varies inversely with the pressure at a constant temperature. So in other words, we're identifying all four things here. So we have the number of moles. They're talking next about, in this, the number of moles, they have that the volume was next, I think, in our list. Then they had pressure, and then they say something about temperature at the very end. That's one of the gas laws I just erased, but that's okay. It's not the right one. Okay, so they say fixed. Okay, so we're not changing that. These two are inversely proportional. Right here it says inversely proportional for those two, and this one is fixed. Okay, not changing. So it's only of the four things. It's a law only about those two: volume and pressure. So they're saying that the product of these is a constant. So up there I say A times B is a constant. Here we're saying pressure times volume equals K. And in science or chemistry, a K is a constant. It could have different values, but it's just a symbol for a constant. So P stands for pressure, V stands for volume, and then K is some value. Okay? It's not always the same in this situation. So here is your first law. Okay? So the one that's like this is they put pressure first. I learned it the other way around but it doesn't matter, right? A times B is equal to B times A. Yeah, so P times V is equal to V times P. So if I measure the volume and the pressure under one situation, and then I change the volume or change the pressure, I'll get a new volume. But this product has to be equal to this product. Why? Because we still have the same number of molecules and they're moving at the same average speed. So P1 times V1 equals P2 times V2. So one is what you have at the start, and the next one is what you have under a different setting, let's say it that way. So you're going to have this syringe, and then you'll use different volumes. It'll go all the way, I think, from, 2.5 milliliters, maybe up to 15 milliliters, we'll adjust it and measure what happens to the pressure. So here's our sample problem that puts this to practice. It says we have a sample of oxygen, has a volume of 150 milliliters, when its pressure is 0.947 atmospheres. What will be the volume of the gas at a pressure of 0.987? So the pressure's gone up slightly, right? If the temperature remains constant. Okay, so if they hadn't said that, then this law wouldn't necessarily help us. So they have to say the temperature remains constant. So let's just mentally think about what kind of an answer I would expect. So notice that the pressure has gone up slightly. So what should happen to the volume? Remember, they're inversely proportional. So what should happen to the volume? If the pressure went up slightly, the volume should, what?
Go down slightly.
Go down slightly. So we expect our answer should be a little less than 150, we think. No, it's not going to be like 10 or anything like that. It's a lot less. Okay, so first of all, we always list our givens. They gave us 150 milliliters. And here's how I would suggest you do it when you're listing your givens. If that's the very first volume given, call it V1. And then they gave us a pressure. Well, that's the first pressure given. Call it P1. Then they want to know what will be the volume. Okay, that's the second time we've talked about volume. So that's going to be V2. And then they talk about another pressure. That's the second time we talked about pressure. I'm going to call that one P2. So here's my two givens. I just have it in a different order than I talked about here, but it doesn't really matter. So there are all my facts. There are all my facts. And then all you have to do is write down the equation. Now, some of you will be able to just put the numbers in here and do just fine. If math is not your strong point, I would suggest that you do this, that you take this equation and solve for what you don't know. And I don't know why it is that way, but this is what I've observed over many years of teaching, that you guys are a lot better at switching letters around from what you learned in algebra than you are at switching numbers around. I don't know why it is, but so switch the letters around. In other words, solve like this one for V2. If I want to solve for V2, I need to divide both sides by P2, right? So that P2 would cancel out. So V2 is equal to P1 times V1 over P2. Okay, that's what I have up there. So whichever method works for you. If you can deal with this just fine, don't bother with this other step. I don't need to do that other step, but I can. Okay, so then I put my numbers in to their appropriate spot. Now, if I did it without using that equation, but this first equation, I would write down, pressure 1, which is 0.947 atmospheres, times the volume, which is 150.0 milliliters, is equal to pressure 2 which is 0.987 atmospheres times V2. Okay? So you can either do it like that or like this, either one. I know from experience that this times this divided by that. I can just do it on the calculator. One thing that maybe I'd like to encourage you is some of you I know will do one step and then you press enter, then you do the next step and then you press enter. Save yourself the time, you know. Just say 0.947 times 150.0 divided by 0.987, and now press enter and you'll have the answer at the end. Okay, so save yourself a little work. Because some of you are writing that answer down and then then you have to enter it in. That's kind of the cumbersome way, I think. And if you make a mistake in copying numbers, your answer's not going to be right. So if you can prevent yourself from having to write down intermediate answers, that's always safer that way. Landon.
Does it matter what way we do it?
What?
Do you care which way we do it?
Well, all I want is the equation anyway. From there on, how you do it math-wise, I don't care. So remember that, this is for Quentin, he already knows this, but just remember that listing your givens, everything from V1 down to where it says V2, I call that work. You don't have to tell me where all the numbers go. Okay, that's all that you need to show me for work. Because I think most of you have a lot of practice from algebra putting in a value in for a letter to solve it. So you already know how to do that. I'm not testing for that. I just want to know that you have it set up right. So 144, is that slightly less than 150? Yep, so our answer sounds reasonable. Now if you'd have gotten an answer that was bigger, that would have been your first clue I did something wrong. Because we already thought it should be smaller, and I'm getting an answer that's bigger. Okay, I did something wrong. Or if it's a lot smaller, maybe I came up with 14. Well, that sounds like maybe a decimal error. Maybe I put the decimal in the wrong place in my calculator or something like that. Okay, so now let's talk about the next law. And this is on this one, let me take this stuff away for right now. So on this one, the number of moles is the same, but on this one, it's between volume and temperature. So it's between this one and this one, okay? And pressure is kept constant, okay? Pressure is kept constant. So it's just between volume and temperature is this new one. And so you probably know this. If you warm up a balloon, the balloon gets bigger, right? Especially if you buy it at this time of year. You go to a party store, buy your party balloon, and they fill it up, but it's cold outside, and I take it outside, and it's all wrinkly. And then I put it in the car, and then as the car warms up, it starts puffing back out again. Then I get out of my car to go inside, and it shrinks again because the temperature went down. The number of molecules in the balloon is staying constant. Okay, it's not shrinking and getting larger because the number of molecules is changing. No, we have it sealed tight. It can't happen. So the temperature is what's changing the volume. So at higher temperatures, the gas molecules are going to move faster. If they move faster, they're going to then collide more often, right, with the container, and that's what pushes the balloon out and makes it nice and puffy. When you cool it off, the molecules don't move as fast and they don't push out on the outside as much, and so air pressure on the outside, which is still always there, pushes in on it and makes it wrinkly. So you need to have a flexible container, and I think one of these birthday balloons is a perfect example of a flexible container because it can change its size and shape. Even a rubber balloon or a latex balloon would do the same thing. Okay, a guy by the name of Charles is the one who did some experiments with gases, where he found out the relationship between volume and temperature, I'm sorry. And here's what he found out, that the volume changes by 1 over 273 of its original volume for every degree of change, temperature change. Now that sounds complicated, I know, saying it that way. So in other words, if you had a volume of gas at a certain temperature, if it went down 1 degree, its volume would go down by 1 over 273. Not that fraction of it, but it would now be like 272 out of 273. In other words, it went down by 1 over 273. It went down 2 degrees, well, it would be double that much. So now, that 273, does that number sound familiar to you? Do you remember what it had to do with? It's been on the board for a couple of weeks, or over a week, but I erased it this class period. Remember this relationship? The Kelvin temperature is equal to the Celsius temperature plus 273. There's that number. Actually, when they were doing Charles' law, here's what I just said. It'd be, when it's at its, if you went up 273, then it would be like double the volume. So when we graph this here, here's the graph. I can see it on my screen, but that's the next slide. If I were to graph volume against pressure, and when the pressure drops to 0, you'd think the volume would drop to 0. And if you would graph volume against temperature, as the temperature goes down, the volume decreases, and if you just continue the graph on, you would think it would get to 0, like the volume would become 0. But what's wrong with that logic? Can you cool a gas off enough to make it disappear? No, you still have the atoms and molecules, right? They still have size. So there is a limit. And if it's a gas, if I cool it off enough, it's going to become a liquid. And are liquids compressible? Now, if you've ever been in the pool and you take and slap your hand down really hard on the water, it doesn't compress well, does it? It stings your hand. Okay? It doesn't compress well. So we know that the logic of this was wrong, because once I get it down to a certain pressure, it's going to turn into a liquid and it won't compress anymore. But it allowed us to think of the possibility that the volume actually, maybe there is a coldest temperature possible. And that's got us thinking about, what kind of temperature scale can I use for this new law? Okay, so the new one is going to be volume 1 over temperature 1 equals volume 2 over temperature 2. And that's provided the pressure remains constant and the number of moles remains constant. So it's volume over temperature. Now, what kind of numbers can you not use in the denominator? Can't put 0. Okay, so we can't have a temperature scale that has 0. Well, Celsius at this time of year, we hit 0 quite often, right? Probably every day lately. And it goes past 0, past 0, past 0, past 0. And what if I put negative numbers in here? That means I might end up with negative volume. What's a negative volume? I mean, there really isn't any such thing. I always say is it like a hole that you've turned inside out? What's that? I don't know what that is. Okay, we'll stop right there.
You can't put negative numbers either.
So you can't use negative numbers either. So we need to have a temperature scale that, oh, you got it all done? Well, good for you. A temperature scale that doesn't have negative numbers. And 0 is not possible.
Yeah.
I figured out how to do the limiting the
Oh, yeah.
So it's just these few questions.
Are all these right?